Hello class, and thank you for watching the second part to 6.3. We're going to begin in this section going over basic properties involving the number 1. And the first one that we have right here is the case that if we have a log base b and the value of the log matches to that base, the answer is going to be 1, because by exponential definition, that would mean that b would have to be raised to the first power in order to get that 1 factor of b. So for example, look at example 4a. Here, the answer to this is going to equal to 1 because our base here is 7. So this base of 7 needs to be raised to the power of 1 in order to equal to that value of 7, to this value right there. So this is going to be our answer for that. And the same thing is true if it's a natural log. Since the natural log technically is the log with base e, and we're evaluating that log base e at e, then this is also going to end up equaling to 1, because like I mentioned earlier, this base e needs to be raised to this power of 1 in order to equal this value here. So that's the first property, the first basic property of logs involving the number 1. Now the second basic log property involving the number 1 is if we have the log base b of 1, that solution is always going to be 0, because b to the 0 power is the only way to get the value here to become the value of 1, is if b is raised to the 0 power. So regardless if it's the natural log or the log, here I want to take the natural log of 1. So my answer would be 0, because the base here is e. E would have to be raised to the 0 power in order to equal 1. Similarly, again, in this example, log base 8 of 1, that equals to 0. And again, because 8 needs to be raised to the 0 power in order to equal 1. So that's the second basic property of logs involving 1. Now let's talk about the inverse properties of logarithms. For any base greater than 0, any positive base that's not equal to the value of 1, if we have a log base b of to the x power, those two things will quote unquote cancel each other out. For lack of a better word, they end up canceling each other out. And this is going to end up becoming simply the exponent. So you end up with the value of x. So for example, look at 5a and 5b. Since we have the log base, here we have the log base 4 of 4 to the 5th power. Since these two values again match up, that value is going to end up being the exponent of 5. And the same thing with natural logs. Natural log of e to the 5th power. Recall from the previous one, the basic properties involving 1, this would equal to 1. Well, because of this exponent right there, that's going to end up equaling to 5, because that 1 will be multiplied with that 5. I won't get into the details of why it multiplies with 5 until the next section, but we end up multiplying by 5, so there's the answer. But in very simple layman's terms, whenever the base of the log and the value of the log are the same and it has an exponent, that will simplify again to whatever the exponent is. Now the second property states that if we have an exponential equation and the exponent to that power is a log with the same base as the base of the power, then those are going to, again, for lack of a better word, cancel out, and the only thing that's going to be left is the value of the log that's in the exponent. So for example, this one right here, let me zoom in into 5c. Here we have a power where 6 is the base. Our exponent is log base 6 of the value of 9. So I hate doing that, but it does that. It quote unquote cancels and reduces out, and the only thing that's going to be left is the value of 9. Similarly, again, with natural logs, natural log and e, again, are inverses of each other. So here our e is being raised to the natural log of 7. And again, I'm just going to write it over here on the right just for notation purposes. The ln, natural log, is the log with base e. But of course, you don't have to rewrite it, just as you understand that these two things are inverses to each other, because again, the base is the same as the base of the log is the same as the base of the exponential expression. Those will do that, and you end up again simply with the value of our log, which is 7. Now, the domain, let's talk about the domain of logs. The domain of a log function in the form of log base b of x is the set of all positive real numbers. So in general, the domain of a log base b of x of gx, where g of horizontal shift, then the domain is going to be determined by figuring out the inequality and solving the solution again to that horizontal shift, along with any possible horizontal dilation. So if I want to find the domain to a function, regardless of what the base is, all I simply need to do is get the x plus 3, get the transformation that we're doing horizontally, any horizontal transformation, which in this case is just x plus 3, that's shifting the graph 3 units to the not positive direction, to the negative direction, and see where that's going to put the vertical isotope, in other words. Recall that the graph of these things, this one right here, is going to shift this graph 3 units to the right. So it's going to have a vertical isotope right here, like this. And again, because there's no horizontal reflection, the graph is going to be still pointing again to the right side. It's going to be on the right side of the vertical isotope, again moving away from it towards the right. So all my x values are going to be greater than -3. Algebraically, we solve that by simply getting again that horizontal transformation, the x plus 3, and have it be set greater than 0. So solving this inequality, we'll get that x would have to be greater than -3, which is exactly what I was illustrating here in my diagram on the left. So this is your domain. Okay, let's skip the part about the domain on the previous page and let's go to the next page here. And we'll talk about the domain later on in the video. So here we have the graph of a log function, and we want to graph a log function. Well, recall that a log function simply is the inverse to an exponential function. This means that the log function reverses the coordinates to the exponential. It also means that the graph of the log function is a reflection of the graph of the exponential across the line y is equal to x, which is this diagonal line right there. So let's review first what an exponential function will look like, and then we'll compare it again to the graph of a log function. So let's look at this right here. So right here we have the log base 2 of x, and if we're going to get the inverses, that means that 2, the base of 2, would be raised to a power, and that's going to equal to the value of y. So the inverse to a log base 2 of x is the exponential function, we'll call it g, where the base is 2, and that's being raised to the power of x. So you see, the inverse to a log is an exponential with the exact same base, and vice versa. So let's see what this graph looks like. Well, you recall that this graph has a horizontal isotope, so imaginary line right there, which is at the horizontal isotope is the y-axis. I'm sorry, not the y-axis, the x-axis. Y is equal to 0 is what I meant to say. Y is equal to 0. So let's plot some points here. So we plot these points. Let's do the same points that we did the first time that we graphed these exponentials from negative to positive 2. We're going to see that the y values are going to be, let's start with 0. That's going to be 1. 2 to the first power is 2, and 2 to the second power is 4. So 2 to the negative 2, that would be the reciprocal of 4, which is 1 over 4. And 2 to the negative 1 will be the reciprocal of this, so 1/2. So let's plot those. And if you recall, and I'm going to do it really thin, and this is what the exponential function will look like. We'll have a point right here at 0, 1, at 1, 2, and at 2, 4. We'll even have a point here at 3, 8. Okay. Now, our log function is going to be a reflection of this line here across this diagonal. So let me just finish drawing this diagonal. So across this diagonal, this is the equation y equals x. So that means that instead of having a horizontal asymptote, you're going to notice that this graph is going to have a vertical asymptote at through the origin. So at x equals to 0. So we now have a vertical asymptote at x equals to 0. Because in order to flip this line across here, it needs to go down this direction. And to flip that portion of that horizontal line across this red line, it has to look like this. So we're going to end up with a vertical asymptote through the origin. So that the equation of that line is x equals 0. Now, because these two things are inverses to each other, then that would simply mean that if I flip the x and y values, those would be the coordinate for our log function. And let me do them in a different color. Let me do them in blue here. Let me pick a thicker color as well. So x, y, and if I flip these 1/4, 1/2, 1, 2, and 4, the y values would be 2, 1, 0, -1, and -2. And let me plot those points. So -2, I have a point over here, -8, and 1/2 would be -1, 1, 0, 2, 1, and then 4, 2. Actually, a lot. Oh, 2, not 1. I plotted that point in the wrong place. And there. Okay, so that's what this graph looks like. So you'll see again how these two things correlate to each other. And now the cool part about this is when we actually evaluate this. So look at this idea right here. So let's see again, all I did was flip these values because like I mentioned, they're inverses. But if I evaluate my function, my f function, let's say at the value of 4. If I plug in 4, I have the log base 2 of 4. Notice that the answer to that is equal to 2 because I need 2 factors of 2. 2 needs to be raised to the second power in order to equal to that value. So that's what the answer is. And again, notice how it matches again that value right there. And when I evaluate my function at 0, log base 2 of 0, the answer, I'm sorry, at 1, not 0, because that doesn't work, 1, the answer is 0. I was looking at the wrong thing. Right here. You see how it matches up to that? Because 2 needs to be raised to the 0 power in order to equal to 1. So you see the math and again the inverse properties again correlate and align perfectly to each other. So therefore, this is exactly what this graph is going to look like. Now, interesting enough, again, notice that the y-intercept of the exponential is now the x-intercept at 1, 0. And notice that when the base and the input value are the same, like in this one, let me move this up. And let me make it smaller. That it ends up equaling to 1. So if I evaluate my function at 2, notice that these two values are the same. And by the property that we mentioned in the earlier part of this video, the answer to those scenarios is going to end up equaling to 1, which again is exactly what's going on at this position right here. When x is equal to 2, the y value is 1, because again the base and the input value match up. So very, very cool again how the graph again works, that how inputting these values matched up exactly to, like I mentioned earlier, the inverses of this thing. So it becomes the opposite. So let's look at this example. So the inverse to this graph right here would be the exponential function g of x equals 5 to the power of x. So, and because the input values and output values to g at -2 is 1 over 25, -1 is 1 over 5, at 0 it's 1, 1 it's 5, and then at 2 it's 25. You'll have again your exponential function. The inverse to that will switch those coordinates and get you the following. So for the log base 5 of x, the x value of 1 over 25, that equals to -2. The inverse 1 over 5, that gives you a -1. At 1, the y value would be 0. At 5, the y value would be 1. And at 25, 25, your y value would be 2. So we're going to end up again with, I'm going to draw this one in black. We're going to draw a vertical isotope right here at 1 over 25, which is really close to that red line. You're going to have a y value of -2. At 1 over 25, again, you're going to have a y value of -1. And this is where it starts to grow a lot slower at 1, 0, 5, 1. And at 25, which obviously doesn't fit here, the x value of 25 isn't on the graph. It only goes up to 10. It's going to look, it's not going to be able to be plotted. So the graph is going to end up looking like this. So as you see again, notice again some of the characteristics, similar characteristics to this red line and the blue line that we have up here. Notice that at the value of 1, and I'll highlight over here on the coordinate grid, on the points, not on the coordinate grid, but on the points here, that at 1, your y value is equal to 0. And the y value is 1 whenever the input value matches up to the base. So notice that here we get a y value of 1 whenever 5, this time at 5, because that's what the base is to this log. So they do have that in common, and that we're going to use that concept in order to identify what the key points, again, those 2 points are going to be, and use those points in order to transform the log function by doing horizontal and vertical shifts and things of those nature. So let's talk about again those transformations on the next page and the characteristics to these log functions. So let's look at the characteristics of these log functions. First of all, the domain of these things, as you saw in the previous example, these graphs only exist to the right of the horizontal isotope, meaning that the input values only have to be positive numbers, as you see on both of these graphs right here, and the one right here in blue and the one right here in red. So what that means in terms of what x values we're allowed to use, we're only allowed to use non-negative input values. So non-negative, which means that the values of x all have to be greater than 0. They can't equal to 0, because remember there's a vertical isotope on that line of x equals 0. Now the range of these functions go from -infinity to +infinity. You see this one right here in red. This is going to continue moving downwards all the way to -infinity. And this one, even though I didn't do a great job in drawing it, it's always going up. So as x is increasing, unbounded, the y values are also unbounded. They're going to go all the way towards +infinity. So the range here is going to be all real numbers, which makes sense because these are the inverses to exponential, so they're going to be the opposite. The domain becomes the range, and the range becomes the domain, which again is the opposite of what we saw when we're looking at the section on exponential equations and the graphs of the exponential functions. Now, the graph of all log functions of this form, f of x equals log base b of x, pass through the point of 1, 0. So they're all going to have an x-intercept at the value of 1. The reason for that is because, let me zoom in, the log base b of 1 always ends up equaling to 0 because of that. Now, if b is a number greater than 1, then f of x equals log base b of x is a graph that increases to the right and strictly increases to the right, meaning that it's going to be invertible. Therefore, an inverse is going to exist. Now the graph of f of x equals log base b of x approaches but does not touch the y-axis, this vertical line right here of x equals to 0, because that vertical line is a vertical isotope. And the other thing, again, just to remember our basic property, involving 1, that if I have the log base b and I input the value b there, the answer is always going to be 1. So at this b value, log base b of x, the output value will end up being 1. So there's always going to be this point, x coordinate b, that will give you an output value of 1. So we can use those 2 points, those 2 key points, in order to transform functions by shifting the graph up, down, left, and right, doing, again, vertical dilations, horizontal dilations, doing also the reflections, horizontal and vertical reflections, and flipping this thing left upside down or to the left side of the vertical isotope. Now, I have a quick reference guide, again, to those vertical isotopes at the bottom of this page right there. But let's move on to the next page and let's talk about each type of transformation. I'm sorry, this is a reference card of the transformation. I don't know what I said earlier, but a transformation involving logs and what the notation looks like and how that's going to transform the log. So just a quick reference guide that you have there. But let's go to the next page and let's talk about these transformations one at a time. We'll begin with reflections. So here we have a log function, again, that format that we talked about earlier, log base b of x, where b is going to be some number greater than 1. And we want to do a reflection. So if this is our log, then the function, let's call it g of x equals to a negative log base b of x. This is going to be a reflection of the graph across the y-axis. So it's going to flip the graph upside down. And if we have g of x was instead log base b of negative x, this means that all of the x values will be multiplied by a negative, resulting in a reflection across the x-axis. So let's look at an example of this. So in example 8a, I'm just going to draw the original function. So log base b of 4, so that means if I plug in the value of 1, my answer is going to be 0. So again, that's my y-intercept, like always, 1, 0. My x-intercept, x-intercept. I keep forgetting that I'm not talking about exponential, I'm talking about log functions. So my x-intercept is going to be 1. And the second thing is, again, by the basic property of logs, that if I input the value of 4, so my input value matches my base, then the answer will be 1. So I know I'm going to have that point there. And again, I just want to draw a sketch of this, so I'm just going to connect it again with the curvature, our little upwards curve graph here, and our function will look like this. Okay, now the idea with the other examples is to draw reflections of this graph according with respect, again, to the x or y axis. Like in this next example, example B, because of the negative sign being out there, that's going to be a reflection across the y-axis. So it's going to be a a vertical reflection. So, I'm sorry, I put these backwards. Fix this. My bad. I'm giving you the wrong information. This is a reflection across the x-axis, and this one would be a reflection across the y-axis. What was I thinking? So let's fix that, okay? So let's do this correctly now. So this is going to reflection across the y-axis, the x-axis, a vertical reflection. So that means that this point here, let me highlight it, this point here is going to be reflected across this line. Because it's on the line of reflection, it doesn't look like it reflects at all, so it's going to stay in the same position. But this point right here will reflect across that line, so instead of being up 1 unit, it's going to go down 1 unit, and this graph is now going to be upside down. So this log function will look vertical there, going down again until we get to the x-intercept. And as soon as we get to the x-intercept, it starts to slow down, still decreasing, but it starts to slow down on how fast it's going down. Now let's compare that to letter C. With the negative sign on the inside with the x, that's going to be a horizontal reflection. So that's going to draw the graph on the opposite side of our vertical isotope. This one here, the vertical isotope is right here, that doesn't move. On this example here, the vertical isotope is in the same place. And in this one, the graph is going to be reflected across the vertical isotope. So instead of pointing to the right, those points of 1, 0 is going to jump across, and it's going to be a negative 1, 0. And the other point, 4, 1, is now going to jump across and be at negative 4, 1. So these points, oops, I don't know why I erased it. Let me connect them again in that curve. The graph will look like this. So this is what a horizontal reflection will look like. Now, if I want to do both a horizontal reflection, like we did right now, and also a vertical reflection, since this part right there looks like this, putting just simply a negative sign in front of that, so putting a negative sign in front of that, it's going to simply flip this upside down. So it's still going to point to the right, but instead of moving upwards like this, it's going to put this point down here and connect the graph like this. So these points are going to be flipped upwards, while these points here are going to be flipped downwards. So doing both a vertical and horizontal reflection, we'll have our vertical isotope here, and the graph from the previous example is now upside down, and the graph will look like that. So this is your reflections. Okay, now let's talk about vertical translation, sliding things up and down. So again, we have the normal notation of our log function. Let's say now we have the log function g of x, and we want to add a value to this. Let me put parentheses on x. I want to add something to this. We're going to add k. Then adding k is going to move the graph upwards k units. Now if I subtract it, then it's simply going to move the graph in the opposite direction and move it down k units. So this is the notation to do a vertical translation. Now, because we're moving again the graph up and down, and the vertical isotope again is vertical, moving a vertical line upwards still keeps it in the exact same position. So this vertical isotope is not going to move. It's still going to be in this place right here. Now, normally, without this -4, okay, without that -4, the log base 3 of x has the following x and y values. So I'm going to make a table of x and y values. When x is equal to 1, the y value is equal to 0. Our x-intercept is at 1. And the second thing, because the base is 3, that means that when the input value x is 3, the output value is going to be 1. So normally we have a point here and a point there. Now because of the -4, what this is going to do is simply move those 2 points 4 units down. So 1, 2, 3, 4. So those points are going to be located there. Notice specifically where the x-intercept has been moved to. The x-intercept was here, and it's now 1, 2, 3, 4 units down. The point at 3, 1 moved 4 units down. 1, 2, 3, 4 is now there. So connecting those 2 points, the graph with this vertical shift of 4 units down is not going to look like this. So we'll compare it again to this one. This one has +4, so instead of moving down, the graph is going to move up. The vertical isotope doesn't change because moving it up or down, the vertical line stays in the exact same position. But this point of 0, 1, and 1, 3 are going to move up 4 units. So let me connect them first, and let me move the entire graph 4 units up. Well, you know what? No, let me just move the 2 points up, and then I'll connect them. So let me move this up 4 units. So 1, 2, 3, 4. And now let me connect those points again using our inverted J. So there. So there is our f of x function. So let's see, pause the video and now try these 2 examples. So let's check your answers now. So for this example, letter C, our vertical isotope will be here at this position. The x-intercept of 1, 0 is going to move down 5 units. So 1, 2, 3. So 1, 2, 3, 4, 5. So right here. And because the base is 3, that means that log base 3 of 3 equals 1. So when x is 3, the y value is 1. So 3, 1, which is right there. That's also going to move down 5 units. So 1, 2, 3, 4, 5. So right there. Okay, so there you have that one. Now let's check your answer for the next one. So here the vertical isotope is going to be in the exact same position. And then the x-intercept is going to be shifted 5 units up, which move it right there. The point 3, 1 will be moved 5 units up. We're going to slide it, translate it 5 units up, and it'll put it there. So there is the graph, a rough sketch of the graph of log base 3 of x plus 5. Okay, so now we finished again vertical translations. This brings us to the last one, horizontal translations. The notation for a horizontal translation is, let me zoom in, would be g of x equals log base b of x plus c, or log base b of x minus c. So we're still adding or subtracting, but this time we're adding or subtracting again to the x values. And like with any horizontal translation, adding is going to move the graph in a negative direction, so to the left, and subtracting moves it in a positive direction towards the right. Now, this correlates again perfectly to the domain, as we'll talk about it in a bit after this. So because of this, because of these shifts right here, the horizontal isotope is also going to move. The horizontal isotope is going to be located at c equals c if it's a positive number, or c equals negative c if we're moving it again in a negative direction. So if we're moving it to the left, it'll be negative c, and if it's moving it to the right, it'll be positive c. So let's look at the example that we have right here on 10a. So here I have the log base 5 of x minus 5. So let's ignore the x minus 5 right now, and let's just talk about the log base 5 of x. Well, if that's the case, when x is equal to 1, the y value would end up being 0. Again, our x-intercept would be that point right there. The vertical asymptote would be located here on the origin, going through the origin, which is at x equals to 0. Our x-intercept would be located right there at 1, 0. And because the base is 5, that means that when x is equal to 5, the y value would be 1. So 1, 5 would be another point that makes again the graph. So just using those 2 points, I could connect them again with my inverted j, and this is what the graph would look like for this function right there. Okay, the x minus 5 is simply going, x minus 6 inside here is going to shift the graph 6 units in a positive direction. So we're going to move all of this 6 units to the right. So let me just do exactly that. So 1, 2, 3, 4, 5, and 6. Oh, I didn't get that last part right there. Hold on. Hold on. Let me highlight it all. There we go. Okay, and let me move all of that. 1, 2, 3, 4, 5, and 6. So you see, look at this. Notice that it's moving again this entire graph 6 units to the right. Move the vertical asymptote 6 units to the right. Move the x-intercept to 7, 1. And move this point from 5, 1 to now 6, 1. So our x-intercept is 6 units higher, so 7, 1. And this point is now at 11, 1. I'm sorry, 6, 0, 7, 0, 7, 0. So now, if it's plus 6, that's simply going to move this entire graph 6 units to the left. So moving the horizontal asymptote 6 units from 0, we'll move it here to negative 6. Moving the x-intercept from 1 to 6 units to the left, we'll move it to negative 5. And moving the coordinate 5, 1, 6 units to the left, we'll move it to negative 1, 1. So let me just connect these 2 points. And there is your graph. So let's look at the example C now. So example C has the same log base 5, but this time it's x plus 3. So that's going to move the graph 3 units to the left. So beginning with the vertical asymptote, the vertical asymptote is now going to be at x equals negative 3. Our x-intercept 3 units to the left will be there. 2, 3, 4. And our other point, 5, 1, 3 units to the left would be there at 2, 1. So let's just connect these 2 points with our little inverted j. And there is the log function of this thing. Now, the interesting part of this, because we're doing things and we're shifting, translating this graph horizontally, notice that the domain of the graph has also been shifted. Normally, the only values of x that we're allowed to use, again, are going to be numbers of x that are going to be positive, not negative, so greater than 0. But because of the shift, that is now going to make all of the y values greater than the opposite of this value, which is negative 3. So it's going to affect, again, the domain of this thing. So keep that in mind when we talk about the domain after these graphs here. So for the last example, for letter D here, this is going to translate the graph 3 units, but now in a positive direction. So it's going to put the vertical asymptote here. The x-intercept is going to be 3 units shifted to the right, so there. And the graph shifted, the point 5, 1 shifted 3 units to the right would be at 8, 1 instead. So this is the graph when we translate it 3 units to the right. Oh, but this is a log base 4, my bad. So I need to, no, let's just change that. Let's change this to a log base 5. So I don't have to redraw these points. So log base 5 of x minus 3 will look like this. Okay. Similarly, again, to this example, to identify this, you know what, let's change this. Let's update this to log base 4 of negative 2x plus 5 instead. So not only do we have a horizontal translation, shifting the graph again to the right, or maybe even to the left. I think this, to the right, no, to the right, and a vertical dilation of negative 2. Let's see how that's going to identify the domain. So instead of relying on the graph, I'm simply going to focus again on my horizontal transformation of negative 2x plus 5. Have it be greater than 0, and then solve this inequality. So we will subtract 5 from both sides, divide by negative 2. So we'll get positive 5 over 2. And since we divided by a negative, that's going to switch the inequality to that. So my domain would have to be the values of x greater, less than 5 over 2. I forgot that I had switched that. So there is how you find the domain to a log function. Simply focus on your horizontal transformation. See what values are going to make that, this one right here, horizontal greater than 0, and then you just simply solve your inequality. Okay, so that concludes our second part to this lesson. I hope this video was helpful. And like always, I appreciate you watching, and I hope you have a great day. Goodbye.